So hi everyone again. If you don't remember my name, Thomas. I'm working with the Mass Honeynet chapter. So this is work related to what we are doing in the new chapter. So yeah, I'm working with virtualization stuff, and this is a lot of this work I actually did for my PhD studies at UConn, which I just finished last September, and the graduation ceremony was just this Sunday. So this is pretty new stuff. So thank you. So yeah, so briefly what we're going to talk about today is why would you want to do this stuff with a hypervisor. We're going to look at some basic anti-sandbox tricks and how do you actually do this stuff with a hypervisor. And then we're going to look at problems that you have when you're using a hypervisor for this, how you can overcome some of those problems, what are left as more work, and then some conclusion. Briefly, you guys are all familiar with sandboxes. Basic idea, let's just throw this binary into this magic box and see what happens. We have no idea potentially about the binary, what it's doing, so let's just execute it and see what we can do with it. The problem is a lot of the tools that are built for this type of work are just our normal debuggers, right? That's really what originally people used for figuring out what a binary is doing. Just you fire up your debugger. That is not going to work necessarily in here because that debuggers assume that the binary is not malicious and it's not trying to work against you, right? It assumes that you just have bugs in your software, and if something goes wrong, it's not because of malice, it's just accidental. Furthermore, debuggers have a problem with stealth, right? You're not going to try to hide the fact that you're using a debugger when you're trying to debug a binary, which is of course not the case when you're dealing with malicious binaries which are actively trying to detect if they are being monitored. So if malware can detect that you're monitoring it, then you have the observer effect. It's going to change its behavior. So how can you effectively observe the behavior of a binary without giving off the signs that it's being observed? If you look at this random strings that you can find in multiplug, which is probably not the most sophisticated malware out there, what you can immediately tell is that it's probably looking at its environment and tries to detect if any of these processes are present in the environment it's running at, right? It looks for process hacker, various VMware processes, virus shards. You know, this is the sort of environment you would assume some malware analyst might have installed in its, little NICE's virtual machine. So if any of these are present, the malware will just shut down. And that's a problem, right? We don't want that to happen. There are a lot of other things that you can look for. There's actually like YARA signatures you can download and run to see if you are running in any of these environments. Some of these are pretty arbitrary. I mean, Tequila Boom Boom, I don't know how that relates to, malware analysis, but apparently someone used that as its username. Malware actually started to look for it, and now it's like, part of this giant signature base of, detecting an analyst who is doing malware analysis. So there's a bunch of things like that. And that's sort of an architectural problem we have, is that if you're trying to analyze malware and we're running in the same context as the malware, as for example Cuckoo does, we end up with things like anti-Cuckoo that can look for the processes in the same environment and even try to crash it. So as far as I know, this has been fixed, this particular one, but it's still an architectural problem, and that's shared with antivirus systems as well. You're running in the same context. Yes, Jurian definitely wants to address it.
So this, some of these things are still working, and that's for a really basic architectural issue. So like when Cuckoo runs malware, you have like malware, Cuckoo, and then Windows. Whereas with the hypervisor, you just have malware and Windows, and you look at it. So we're kind of doing man in the middle, sort of, I would say. And they're just looking at it. And this anti-Cuckoo was developed by a great open source, project person who really wanted to make it much easier even easier for malicious people to detect the code. So great.
Well, right. But I mean, it just shows that there is architectural problem, that if you're running in the same context as the malware, you're kind of playing a cat and mouse. Who is going to dig deeper into the kernel of that virtual machine to place the hooks deeper? And you cannot really, say with 100% certainty that you will be the one that can win that race. So what you should be doing is something else. So when I was making this slide, I figured like, well, no real malware would actually try to, just crash cuckoo, because that would be quite a visible artifact. If something crashes cuckoo, that's usually probably a bad sign, until I actually looked at what the hacking team did, or the hack team. They exactly did that. They were just crashing cuckoo. So
that, by the way, doesn't work anymore for 2 years.
Yeah, so this one is fixed. But yeah, so they were pretty much just, whatever, let's just crash cuckoo. If they were a little bit more sophisticated, they would have probably just tried to falsify the results, just sleep or something, so that they don't actually stand out. So what can we do to improve this stealth problem? There was a couple honeypot developed here in the Honeynet project, the SEBEC and Quebec honeypots, that actually used additional layers. So for example, the SEBEC honeypot moved things into the kernel. So effectively developed a kernel driver that you can load, and then it will monitor the execution of that sandbox from the kernel. From architecturally, that's a little bit better because you are running in a privilege mode compared to a process. But Windows actually, with Windows 7, implemented things like PatchGuard, and they really don't like if you just arbitrarily hook stuff using a kernel driver, primarily because antivirus software started doing that, and there were real issues with them crashing Windows, and it was just a bad user experience. So Windows was like, Microsoft was like, yeah, let's not allow that. So it actually scans the kernel memory, so you cannot just use a kernel driver anymore to easily monitor stuff. And again, we are starting to see rootkits more and more often now. So we still have the same problem. We have things running in the kernel. Well, malware loads a rootkit, and now again, who can hook deeper into the operating system? So that's not ideal. So the rootkit problem in 2015, we see things increasing. There are more and more rootkits. But according to McAfee, it's still only 0.36% of all the malware they see. So is that a big problem? The problem with these kind of statistics is how do you actually detect rootkits? If none of our automatic analysis tools can detect rootkits because they are working on the process level and then rootkits can hide from it, it might just mean that we are really bad at detecting it. So 0.36% is what McAfee detects. Whether that's an accurate representation of how many rootkits out there in comparison to all the other types of malware, it's probably a lot higher because simply we suck at analyzing rootkits in an automatic fashion. So that's where we get to the hypervisor level, right? That's even below the kernel. We can get even better visibility into what is happening within that sandbox. It's harder to detect, but it's a lot easier said than done. There's a lot of legwork that you need to do. But anyway, let's look at what it actually looks like in action. So this is a demo that I recorded previously. So I have the Zen hypervisor running here. This is an older version of Zen 4.4. We are about to release 4.7 in the next couple of months. I have Windows 7 running. And effectively what you can do from an external perspective is similar to memory forensics, for example. So you can reconstruct what processes are running within that virtual machine just by looking at its memory through the hypervisor. And the hypervisor allows you to look at the memory because a lot of hypervisors need the ability to migrate one virtual machine from one host to another one, which requires transferring the memory. So we have access to the memory, and unlike memory forensics, we also have access to registers within that system and also live events. So what I've been showing here is pretty much just the memory forensics equivalent, but you can actually do live tracing of virtual machines, and what you actually see here is the system calls that are executing on a Windows 7 system live as I'm actually moving the mouse here. As you see, if I start to move the mouse, I get a lot more events. And the way this is implemented is it's using the hardware virtualization extension, so there is nothing within that virtual machine itself that malware can look for. If it scans memory, it will see nothing. There is no agent installed within that system. Everything is done from an external perspective. That requires you, of course, to understand Windows internals a lot more than if you were within, because you cannot just use Windows API. you really need to understand how things are laid out in raw physical memory of that virtual machine. But that given, you can really implement a lot of really cool stuff. So for example, right now, this is pretty much just the system calls, but you can add extra information, so you can actually trace, for example, kernel heap allocations. These are structures that Windows allocates to keep track of metadata about various types of objects it needs to operate, like, for example, file objects, I/O objects. So for example, I'm moving the mouse, and what you see here is the description I/O allocations popping up, and that's just for Windows to keep track of where the mouse is. So you can actually trace where the mouse is moving within the machine, or you can trace, for example, what type of files are being opened or accessed within that virtual machine without touching the disk. Which is pretty important because a lot of the time, so Windows 7 actually has write caching enabled for the disk, so if you have a malware that has multi-stage droppers in it, it would extract a file, load it into memory, and delete it from disk, so that sample would never actually hit the disk itself, because write caching still had it queued to be flushed to disk, and it would never hit the disk. So you can actually only see a lot of these files if you're looking at the memory. So I just clicked on random stuff, and you can see, you know, all these files popping up that Windows is accessing in the background. And again, this is all done just through monitoring the kernel heap allocations that Windows does live. So I created a file on the desktop, and still, you know, how many things Windows does in the background, like it's crazy. But yeah, so I'm just gonna grab through that output, and you can see that test.txt shows up there, so the file I created on the desktop actually is visible through memory. So that's you know, just getting things up and running. Let's see. Now, if you're moving everything outside, you end up having things made very difficult, even simple things like how do you now start the execution of malware. You have no agent within that system. How can you actually start the execution of a binary that you placed on the disk of that VM before? This is, you know, a problem because we don't want to have anything within this machine that could potentially be fingerprinted as the analysis environment. So we can actually, instead of just observing the state of that virtual machine, we can actually manipulate the state of that virtual machine live to get things working, such as process injection. So again, what we have here, let's hope that YouTube actually upgrades the, there we go. So again, we have a Windows 7 VM here running, and what I'm going to do is I have a process running here that periodically gets scheduled, right? Task Manager constantly monitors the execution of what's happening within the machine. And what I'm going to do is whenever that Task Manager gets scheduled, I can actually hijack its stack and inject a function call effectively to get access to the ingest API of Windows to start the execution of arbitrary processes. Again, you know, simple things like calling a function, doing it from the hypervisor level requires a lot more effort than just, you know, as you would do normally, write in C and then compile. Here you actually need to know how Windows compiler actually sets up the stack for you. But as you saw, I was able to execute calculator.exe within that machine without actually having any special process in it. So here I use Task Manager, but you could use pretty much any other process that's just running in that virtual machine. And that's quite handy. And the way that the API actually works is that it actually functions as like an external shell. So you can actually, you know, make it open up a website and, you know, act as a honey client as well. You can send that virtual machine to just download arbitrary, you know, website data from wherever without leaving a trace within that machine. So that's for Windows. These stuff I have open sourced a couple of years ago already, but you know, we haven't. Yep.
Quick question on Windows. How much effort is it to support newer versions of Windows?
It's quite significant.
Okay. And what versions do you currently support?
So right now it's Windows 7, 32-bit and 64-bit, pretty much any version of Windows 7. Windows 10, we have system call tracing working, but then things like process injection and more specific features like file tracing, that's going to be different a little bit between versions of Windows, so I haven't actually got the chance to get there, but system call tracing works on Windows 10 as well, so that I can say for sure. But yeah, so that's the next thing, is like how do you actually add support for other operating systems, for example, or potentially other architectures. And that's an ongoing effort. So right now, what we are doing this summer, we actually have Google Summer of Code students working on ARM support for this, as ARM CPUs also have now virtualization extensions. So you can actually run virtual machines on mobile devices, and Zen actually supports a good handful of them. So some things are similar, some things are not. So we got some of that working as well. So what I have here right now is actually a pretty new demo that I recorded just last month. What we have here is actually Zen on ARM running on a Zen development board, and this is still the Zen 4.7 unstable. So this is still a experimental feature of Zen that is, I'm just merging it this week to Zen. So again, we still have all those features available for us for accessing the memory of the virtual machine, and that's quite nice because Zen exposes the same API regardless of what architecture you are in. And then you can do tracing of events within that virtual machine as well. So in the right here I have the guest, and on the left I have the monitoring, and as you see I have the system calls trapped. So I can actually monitor the execution of Linux system calls through the virtualization extensions on mobile devices. So you see a bunch of sys get time of day system calls popping up as I'm just poking around on the file system of a virtual machine. It's a lot more visible. For example, if I say ping, you can see the corresponding system calls popping up just as the ping event is happening within the machine. So effectively what that means is that we will be able to do Android malware analysis using virtualization. So having the same features available for not just Windows on x86, but also for Linux and also on ARM. So there's a bunch of really cool things happening in this space. So great, this is awesome. Are we done? Of course, no. The problem we have is, same thing with debugging and debugging tools. Virtualization was not designed to be stealthy. If you look at the requirements that hypervisors have, they don't have to hide their presence. In fact, hypervisors advertise their presence. So a lot of the hypervisors want to let the guest know that it's running in a virtualized environment so that the guest potentially can load better drivers, supporting para-virtualized drivers that use shared memory instead of emulated devices. So hypervisors were not designed to be stealthy either. So either though the monitoring components are not visible, the hypervisor is still, and the fact that it's virtualized is. So what can we do about that? This is a tool called the Paranoid Fish, which is an open source tool that effectively is designed to detect various types of sandbox and emulated environments. And this is just a small snippet of all the things that it checks for. It checks for the Bosch emulator and a bunch of other things. So if you fire it up in a virtual machine on Zen, this is what you see. And red things here are bad. We don't want to be able to, I don't want this tool to be able to detect that it's being traced. Of course, it's a guess from its perspective. It checks for trivial things here. So traced is, a guess from their perspective. That it just means that, hey, this environment looks suspicious. So let's look at what it actually does. It looks for example, the CPU ID hypervisor bit. That's what I was mentioning before. The hypervisor actually advertises its presence for the guest through the CPU ID feature. Other things it will check for is, how much disk space it has, how many CPUs are available, how much memory is assigned to that VM, simple things like that. So let's go through that list and see what we can do about some of these things. So again, CPU ID is advertised, but the CPU ID instruction itself can be emulated. It is trappable to the hypervisor, so this is how the Paranoid Fish checks for. Just issues the CPU ID for this particular vector. And that's nice because Zen actually exposes a nice configuration feature where you can hide various CPU ID flags. So for example, if I just zero out the 32-bit here, then all of a sudden Zen won't advertise its presence anymore to that guest. So, hey, nice, that was easy. So let's keep going. 60 gigabytes of free disk space. How many sandboxes you have that are running with 100 gigabytes of disk space attached to it, right? It's
a lot.
Cool. I mean,
virtual disk space.
Right. I mean, if you can do tricks with it, that's nice. But for example, that's what we do here as well. You can actually do things like copy on write disk, and then you can assign arbitrarily large disk space to that virtual machine and just hope that it doesn't actually going to start downloading Game of Thrones into that virtual machine, because then you might run out of space. So that's what we do as well. So you can do LVM, which is of course a standard Linux file system abstraction tool that supports copy on write, and it's effectively solves this problem, right? We can make the virtual machine just use as much extra space as it actually uses. So that was easy as well. Other things like uptime check. How long has that virtual machine been running? A lot of sandboxes, you actually have to boot the entire machine up from scratch, and then once it's booted, you start executing the sample. Well, that's suspicious. Let's look for things like, how long has it been running, and then detect the sandbox based on that approach. Easy to get around it as well. Create a memory snapshot of the virtual machine. Let it, actually just let it run first for like a couple hours. Create a snapshot of it, and then restore that memory snapshot every time. So if uptime check is performed after, it will see that, oh, this machine has been running for hours. When in fact you just restore that base image from the get-go. Again, this would be fairly simple to fix. Memory size check, again, how much memory you want to assign to your sandbox environment, probably as little as you need, but that could also be a red flag. How many people use virtual machines with tiny amounts of memory? Is that your target environment? Malware may decide to shut down if it doesn't have a virtual machine with 4 gigs of RAM. Of course, if you assign 4 gigs of RAM for every sandbox you have, you will potentially be only able to run a handful at a time and just waste a lot of memory. But you can also do some cool stuff with Zen. For example, there is this feature called memory sharing, which is effectively the same thing that LVM does for the disk, but you can do it for memory. So you can actually share memory between virtual machines. This is a graph when I was performing some high interaction honeypot tests using this feature, and that the black thing you see is like how much memory it would have required to assign for virtual machines, Windows 7 64-bit. So if I assign 2 gigs of RAM for each, how many VMs I could run at the time. So let's say I have 12 gigs of RAM, I could run maybe 11 high interaction honeypots. Now if I should do memory sharing, all of a sudden my 12 gigs of RAM is, holy shit, I'm up to 40 high interaction honeypots. Because depending on how much memory those virtual machines are using, you don't end up using all that much extra memory. And this was actually performed on live worm infections on a university network. So this is like the plus and minus of how much memory the infections were effectively using. So this is real data that I was gathering while my machines were being infected. So this is pretty cool stuff. It's has downsides as well. Over time, the sharing decreases. So if you run it for 2 minutes, then you might decrease the memory sharing down to like 25%. But you can optimize something. So Windows 7 actually did a bunch of things in the background that you can disable, and then memory sharing can be optimized. Or do future work is to do like runtime duplication of memory of memory that has been freed that can be reshared after a while. So this is a cool feature to maximize the effect of your hardware. Again, it's a little bit experimental, and the original developer who was working on it went to work for Google and pretty much just got bought out and no longer around. So I kind of stepped in as the maintainer of this subsystem at Zen and trying to clean it up so that it's actually more polished and actually more usable for this type of experiments. All right, so let's just see where we are. Number of processors. How many sandboxes are running with 2, 4, 8 CPUs? Probably not that many. Most of them are running with 1 CPU, hence the check. Now, for hypervisors, this is actually a particular challenge because a lot of the things that we are doing is manipulating the view of memory that virtual machine has using the extended page tables, which can end up in a race condition when you have multiple vCPUs. To better understand what I'm talking about is, this is the hardware lookup for memory accesses when you have a hypervisor. So up here you would have a process, here you have the physical address space for the virtual machine, and then you have the actual physical address space of that machine in the hypervisor space. So when a guest tries to access a virtual memory, it would first go through page tables and get translated to guest physical address, and then go through a second layer translation using EPT, and that would get you the actual address of where that memory is located. The nice thing about that is that if you modify the EPT permissions here, that violation, any type of violation, will go to the hypervisor. So that's how we can do stealth checking, because we're not modifying anything between the guest's environment, we're modifying the hypervisor environment. That EPT table, though, is shared across all vCPUs. If you modify permissions there, that will affect all vCPUs running in that system. So you can potentially end up in race conditions. So what you have to actually do, you get an EPT violation, you have to clear that memory restriction you have. Let's say you are tracing execution, you get a page fault saying something was trying to fetch instruction from this page that is not allowed. So you need to clear that memory permissions and go through this whole hoopla to continue the execution as if nothing happened. And in here, when you clear that trap, that's where you have a race condition. And that's a problem. Some solutions that other people are doing for this is that you can just pause all other vCPUs that are running on the virtual machine, which is quite a heavy-handed solution. Or, for example, what Bitdefender is doing, they're using this same system to do their own malware analysis suite, is emulate instruction. When you get that violation, you can actually fire up an emulator, a CPU emulator, and just emulate that instruction as if you were running in QEMU, for example. Of course, emulators are buggy, and if possible, we should avoid using it for this purpose. And as of last summer, there's actually a really awesome way in Zen to get over this, and this is the Zen Alt P2M system. This was contributed by Intel, which allows us to actually create multiple page tables down here for virtual machines. So as I said, the problem is that this table was shared across vCPUs. So now instead of having just one table that is shared, you can have multiple tables and just swap around those tables as vCPUs are hitting violations. And this is a really nice, easy way to get around this problem. And it also allows us to do some really nifty things like changing where those memories are mapped. So you can actually modify code within that machine and have it stealthy and support multiple vCPUs. So with that, we get our number of processors up to arbitrary number, as many as your hardware actually supports. So we are actually down to a handful of stuff. Let's see what else we have here. Using mouse activity, I/O activity things. Most of the I/O for Windows at least goes through an emulated device driver to QEMU. So there's a VNC API exposed, so we could actually just emulate pretty much mouse movements and make it look like someone is sitting at the computer. And some people actually did that. There was a study made by the guy who was making Panda doing a bit, where he did an experiment using this feature to click on install buttons. Like you have binaries executing, and sometimes you have pop-ups. Clicking on the buttons that popping up in these binaries, what happens, and what he actually seen in here, study from last year, that it doesn't really make much difference. Yep.
So it depends obviously on your sample set, but
right.
For us it makes roughly a 5% detection difference.
Okay.
So it does make a difference, but this is a lot of grayware. So installers, they only trigger when you go through the install process. So
yeah, I think his problem was that he got a lot of Russian binaries, and then he didn't have the recognition for Russian fonts and wasn't clicking on things that were appearing in different languages, so he only looked at a subset of it, but he didn't seem to have much effect on his. But yes, your mileage may vary. But again, it's all based on emulated input, so you can really do whatever you want. So this is relatively easy to implement. We're not doing that right now, so that's future work. but that's not a roadblock per se. What is a roadblock is telling time. So one of the things that was still left on that list is RDTSC is one of the instructions that reads the timestamp counter, which is used for timing analysis. And that's a problem because RDTSC is exposed to the guest. We can trap it, so we can lie about how much time elapsed between two calls to RDTSC. But the problem is that RDTSC is not the only way to tell time within a virtual machine. So you can potentially tell that, hey, this one function I'm executing that I suspect would be monitored if I'm running in a sandbox is executing way slower than it would have on a normal machine that is not monitored. And we cannot really exclude all of the possible channels that malware can get access to timing sources, especially if you expose a network interface and allow that malware to go through the internet. You can get covered channels. There was actually a talk about here earlier about covered channels. You can get any type of covered channel to get some sort of timing information that you could potentially use to deduce that, oh, you're running in some weird environment where execution time for various instructions is taking longer than it would have without monitoring. So telling time is a big problem that there is no solution for just yet. Let's see what else we have here that we can check for. Yeah, so we have more CPU ID leaks that we can check for. Also, emulated device drivers would reveal that you are running on a virtualized environment. For example, the network card would say Red Hat. Disk vendor leaks, all that stuff. Screen resolution, vendor the files modify, username, GUIP, all these things. Most of these are fixable, right? So none of that stuff is hard-coded. You can modify the disk driver name, you can modify all that stuff. It's just, keep a lot of low-level artifacts to keep track and keep in mind when you're deploying such a solution. But the question is, of course, does malware really care about all this stuff? I mean, no malware is going to check for everything. But there is also a better way for malware to just get around all that crap, right? The more checks they need to add, the easier for you to detect that, oh, there are so many checks here, that's probably a malware. What happens if malware just goes sleeping, right? You can hook the function that they might use for sleeping, but what happens if it's not using the standard API for sleeping? What if it just has, a probabilistic locking mechanism for, before it starts executing its real payload? There are a million ways of stalling the execution of a binary. There is no way of actually getting around that. So that's probably the easiest thing that they can do is like, all right, I don't care about the environment. I'm just going to sleep for 5 minutes. You're probably not going to run your sandbox for an hour on a sample. Simply, there's too many samples, so you can really easily time out the analysis. So that's really a bigger issue. This is effectively goes down to the halting problem. There is no way to tell when a binary is going to expose malicious behavior, the same way as you cannot tell when a binary is going to exit, or if it's ever going to exit. Some other advanced stalling malware I saw when I was doing my analysis on a 100,000 sample set is a pretty interesting one. So instead of just randomly sleeping, you can actually use the sandbox environment against itself in that all that monitoring that you're doing adds overhead. So for example, if you start calling functions in your malware, that normally returns fast, but if you're monitoring, for example, the anti-create semaphore, system call returns pretty fast on normal Windows machines. If you're monitoring though, you add overhead for every time it gets called, so you can actually use that extra overhead to time out the analysis. So I was very interested to see if anyone is using this. This was proposed back in 2011, that Malware is going to use this. I was interested to see if I see any of that in that sample set that I was digging through. So we needed some baseline for that. So after executing 100,000 malware samples, this is like a distribution of system calls that you see. You have a big chunk of system calls here that are pretty much called in every malware, and then you have a long tail of more esoteric system calls that were only present in a couple samples or maybe one sample at a time. So based on that, the average number of calls that I observed for empty-create semaphore was about 10. So out of that 100,000 sample, there was only one that was significantly above this average. When it's called it 17,000 times, which was way above any other sample. So it was quite interesting to see that this technique is actually used that was just proposed in an academic paper 5 years ago. And then, of course, this is just one example of an API that you could use for this. There is a million other things that you could do. So this is actually becoming more prevalent. A couple months ago, Joe Sandbox actually published a blog post about how they are seeing this against their system more and more often lately. So this is where things are heading. To wrap up things, after doing all this stuff for years, what I can tell you is there's no absolute stealth. If you're making more stealthier tools, it may result in malware having to do more checks. But that only holds if you are still using all the lower level tools, right? If by tomorrow every tool transitions to using a hypervisor, malware is going to have an easy time because then it can just throw away all the low-level checks that it had to do for emulation, right? Or checking for the cuckoo process. We want the malware to have to do lots of checks because that bloats it and makes it harder for them to develop. So if you just move everything to the hypervisor, it's not going to solve our problem. Hypervisors are not magical unicorns that just solve your problem. We need to use the entire spectrum of all the tools we have. And to be fair, most of the malware would work normally. Under cuckoo, there is only a small subset that you would really need a hypervisor for. So yeah, so there is no end in sight. There's still a lot of low-hanging fruits we need to work on. And yeah, there is a lot of corner cases, and it's pretty hard to work with a hypervisor. So it's not going to get you a big user community to work on detection plugins simply because you're adding more layers between what the user cares about and how that can actually be implemented. And keeping track of that entire stack is pretty damn hard. So it's not necessarily the best option for everyone. But again, it's open source, so if you're interested in that type of stuff, then definitely check it out. And yeah, so these are both open source. So the libvmi library is the wrapper around hypervisors that allow you to do a bunch of things, and then the dropproof environment is for actual malware analysis based on libvmi. So thank you, and if you have any questions, then yep.
Do you have any statistics on how many malware is actually doing that detection? Because on one hand, more and more solutions are moving to the VM, so there are application servers running on the VM. So if malware detects the VM and stops, it basically shoots itself in the knee because that's a real target. And on the other hand, if the OLEDBG presence stops malware from executing, then I will install OLEDBG on every single account and computer in my company, so they are protected.
Yes, there was actually an academic study on that if you just install Wireshark and a couple debugging tools, you will protect yourself against a good chunk of malware. So that's a legitimate solution. It might be better than your antivirus system.
Any triggers? I mean, what was the percentage?
Well, you saw the strings in that slide that I had in the beginning. So, I mean, install Process Hacker and Wireshark and you're good. I mean, joking, but that's where things are.
How was the percentage of malware actually looking at that?
No, I don't have any hard data,
Okay.
and I mean, I don't know, Julian, what do you see?
It's difficult to say, I guess. Quite some. Do you have studies about that?
Question?
So the interesting thing is, you see the malware. So the malware is trying to detect the sandbox or the hypervisor or Ollie debugger or whatever. But because it's looking for those things, in Google at least we have a couple of signatures. Like, oh, hey, the malware is looking for Wireshark in the registry, on the file system, on the process memory, I mean, in the running list of processes maybe. So we have maybe 2 or 3 dozen signatures just for detecting malware that tries to detect the environment. And already that, I mean, even if it still detects it, that's already a good indicator in a lot of cases.
So that's exactly my point. We want malware to have to check for these low-level stuff. Because if we move everything outside, then malware will stop checking for this, and then we will lose the ability to check for that check. So it's cat and mouse game. So that's why I'm saying use the entire spectrum, force them to check for everything. That's probably the best option we have.
Now we have seen a lot of samples or legitimate programs that do the VM checks.
Yes.
For various reasons. We have to be careful. It's not costly for VMs to have malicious.
Sure.
So we look a lot into samples that do this kind of checks and don't show any malicious behavior, and then we see, okay, they do any additional check that we haven't covered yet, and then we add this to our picture.
Right.
So it's actually really cool. And they're giving away that they're interested about materials that gives you a lot of easy samples to look into for your research.
Yep. Cool.
I have another question. Do you have rough numbers how much overhead your tool puts onto the hypervisor?
It highly depends on how much monitoring you're doing. So it's configurable right now. There's a handful of plugins we developed, ranging from system call tracing to file tracing and all that stuff. So it really depends on what you're interested in. Of course, the more stuff you add, the slower it will get. Just simply because if you're hooking system calls, for example, or kernel heap allocations, that's really in the fast path of the execution of that machine. But as you saw, I was still able to click around that machine and interact with it normally. So it's quite usable. I wouldn't use it in production, but for malware analysis, it's good enough, right? I don't care really on how fast that malware is going to run in that machine. What I care about is that it will run in that machine and will give me the artifacts that I'm looking for. One more important metric, in my opinion, for malware analysis is not the overhead, it's the throughput. How many samples you can crunch on a given hardware. That's your goal, right?
Yeah, but if the VM runs 5 times slower, then I have 5 times slower throughput.
No, not necessarily.
Because I want to run the sample for 1 million.
Right, but you don't necessarily know how long you want to run that sample for. So,
if I know that 1 minute is my sweet spot, I have the highest detection rate.
yeah, no, I mean, of course, if you have overhead, that's how much longer you need to run that VM for. But what I'm saying is that you don't know how long you need to run that sample. Is that going to make statistically, relevant difference that you are, have 20% overhead versus 15? Hard to say. It's in my experience, as long as malware is not timing out when it tries to connect to external servers on the network, it doesn't care, right? It might try to do timing analysis to detect that things are running a little bit slower. But what happens if you're running in a cloud environment where the server is just overcommitted and has a shit ton of VMs running, right? You will have the same type of issue that the VM is waiting for the hardware to schedule its execution. So 20% slowdown might not necessarily be that suspicious. It might just be a busy server. So yeah. Any other questions? Cool. Well, thanks again.